Okay, let's talk about planar symmetry in Gauss. This is the one type of symmetry we haven't yet discussed. So we've discussed spherical and cylindrical, but I just want to touch on planar. And I'm actually not going to do a particular problem. I'm just going to talk about it more in general. So let's say that we have a sheet of charge, right? We're talking about something that is planar. So it's a sheet of charge, and say that we're given the charge density, it would be charge per unit area in this case, which is sigma. So let's say that it has some, positive, let's call that positive 3 sigma on it. And we want to find the electric field, say, just outside the sheet. So one of the things we would have to talk about is the fact that this sheet is really large, and that we're just interested in a little small spot in the middle of the sheet, because as soon as we start getting to boundary condition issues near the edge of the sheet, that starts being a problem for Gauss. So what Gauss is good at is super very, very symmetric situations. As soon as you move away from that, Gauss is not your tool. So these are really the only situations that we use Gauss for. But say we have a really, really large sheet like this. The question might be then, what shape do we use for our Gaussian surface? That's the main thing I want to talk about. So remember that when we use our Gaussian surface, we have to capture some of the charged material inside it. That's really important. If we don't capture any of the charged material, then Gauss's law isn't super useful to us, really, for this. And remember, Gauss's law tells us that epsilon naught times the flux equals the enclosed charge. So here's Gauss's law, right? If I don't enclose any charge, then the right-hand side of that equation is 0. And so that tells me that the flux is 0. Now, that can be useful, like when we're finding the induced charge, we actually use that property all the time. But in a case of finding E, that turns out not to be useful. All we know is that 0, if I enclose no charge, I have 0 flux. So it doesn't bring us to a useful place. So let's discuss about what we can do here. Now, say I'm drawing, um, say I'm where I'm just like kind of looking at this plane. I'm looking at it in perspective view. One of the things that I have to think about is, what does the electric field look like caused by this plane? So this plane has a positive uniform charge density. So right away we can think that, all right, what that means that the electric field is going to look like, again, I'm going to ignore the boundary stuff here, is that I'm going to have electric field is going to be normal to the plane of the page, and it'll be pointing away from the plane of the page. So something like that, right? So up here, it would all be pointing up away from the page, and then down below it, it would be pointing down away from the page. Okay, let's move to, this is a in perspective diagram. Let's move to a side view diagram now. So from a side view diagram, say here's my plane, right? And it's really long, so I'm not going to worry about the size of it. And I'm going to draw my electric field in again here. So, and this is positively uniformly charged. So my electric field this is important because this is going to inform our choice for Gaussian surface, right? My electric field looks kind of like this. And this is for a plane of, I think we said positive 3 sigma is this uniform surface charge. So that's what my plane looks like from the side. So now for my Gaussian surface, I want something that's going to capture some of this charged material. But another property that I want for my Gaussian surface is I want a nice, simple relationship between E and dA. So I'm going to remind us here that Gauss's law tells us that epsilon naught times flux equals my enclosed charge. That's Gauss's law. And then the definition of flux tells us that we care about the spatial relationship between E and dA. So E I have here, that's what I've already written in. Let me label that. That's E. Cool. All right, now let me go ahead and draw my Gaussian surface in. So I'm going to draw it as, I'm just going to use a cylinder position, something like that. So if I position my cylinder like that, what I can see is that the end caps of my cylinder here, I'm going to have a dA that is parallel to my E. Remember, dA is always outward normal for your Gaussian surface. And for the rest of my surface that's cylindrical, my dA is going to be normal to E. So along the curved surface of the cylinder, I'm going to have no flux at all through that surface. The only place I'm going to have flux is through the end caps of the cylinder. Okay, so kind of you have to wrap your head around that. These problems are super spatial, right? So here's another dA, and kind of see this in 3D. It's like a cylinder, like a can, right, or soup can or something like that. That around the curved parts of the can, dA and E are going to be everywhere normal. And only on the end caps of the can am I going to have any flux, any of the electric field that's actually making it through my Gaussian surface. So this is nice because it actually simplifies my analysis here. So if I look at my situation now, I can solve for my flux. My flux is going to be E times, well, let me draw it in like this. The integral of the dA that contributes to flux, right? So that area is going to be the area of the end caps only. So it's going to be, if this is a cylinder, say this cylinder has some radius r. So I can say pi r squared plus pi r squared, for instance. Both the end caps are going to contribute. I have flux through both end caps. So that's going to be 2e pi r squared. That's my flux. My enclosed charge. So I'm enclosing, remember in here I've got an area of the sheet enclosed, right? I'm containing that. And that area is pi r squared. So I'm enclosing pi r squared, and then I'm going to multiply that by my charge density in order to get charge. And remember that sigma is actually charge per unit area. And I just remembered that it's actually 3 sigma that I put in for this problem. Okay, so I have my enclosed charge is 3 sigma pi r squared. So I can put those two things together into Gauss's law. I'll switch up my color. Epsilon naught times flux. Flux in this case is 2e pi r squared is equal to the enclosed charge. The enclosed charge is 3 sigma pi r squared. And here you can see that the pi r squareds are going to go away, and that really all we had to do was call that area, the end cap area. We could have called that like A or something, and then A would have gone away. I'll talk more about that in just a moment. So that pi r squared isn't going to matter. My next move is to solve for the electric field. And what I end up with here, that'll keep my 3 sigma in the numerator, and I'll have my 2 epsilon naught in the denominator. Just let me look at that real quick. So my pi r squared goes away both sides. Yep. So this is kind of interesting. What you might notice here is that this doesn't have an R in it, right? So what this is saying is that this is a uniform electric field, uniforming that it doesn't change with space. And that feels non-intuitive, that like, wait a minute, how can that not change as you get farther away from it? But really, this is not taking into consideration the boundaries of the sheet because of the need for Gauss to have so much symmetry. So we say, if you had a finite sheet, you could say that, well, you could probably make the argument to use Gauss's law for like in the middle of the sheet. But as soon as you started approaching the boundaries, the edges of the sheet, then you would need to use a different method. Gauss's law is no longer your method for that case. Okay, so the only other thing I wanted to mention here briefly was that um, I know I used a cylinder. It's very nice and neat and it works well in this case, but I like to push on this a little bit because a cylinder is actually over constrained for this. So I just want you to notice that it actually doesn't matter what the shape is. I could have like a weird shape thing as long as the sides are normal to the plane, right? And the end caps of the weird shape thing are normal to E. So I'll still have the same case of all of my DAs on the end cap here being in exactly the same direction as E, right? Even if it's like a funny shaped, um, even if it's a funny shaped Gaussian surface. I just have to make sure that these end caps planes are parallel to the plane of the charge sheet and that the sides along here, these sides are normal to the sheet. And as long as I have that constrained, then it can be like shaped like a heart, whatever. It doesn't matter. It doesn't have to be a cylinder. Cylinder is convenient because it's easy. Your brain doesn't have to work real hard to parse it and it's easy to define.